So I'm Mike Arnold, a professor at the University of Wisconsin, and my team has developed a method for aligning carbon nanotubes to create high-performance semiconductors that outperform silicon. This allows for electronics that use less electricity, extend battery life, enable faster computing speeds, and meet the aggressive needs of next-generation electronic devices. So semiconductors are a $425 billion market and really have enabled all of modern electronics. Semiconductors are special materials that could be switched between electrically conductive state. For example, we know that copper wire is electrically conductive, and electrically insulating states like glass is an insulator. And the switching can happen dynamically, billions of times a second, and that's how a computer works. So semiconductors are the basis of chips and microprocessors in all your gadgets, in your cars, appliances, laptops, phones, and so forth. However, the majority of these devices rely on silicon, which is a materials technology more than 50 years old. And silicon is now being pushed to its limit. It can no longer meet the demands of next generation electronic devices. So we have a new approach to outperform silicon and to potentially usher in a revolution in microelectronics by harnessing carbon nanotubes. So carbon nanotubes are thin sheets of carbon atoms, just one atom thick, rolled into a seamless tube. So this nanotube here, in real life, is about 1/1000th of a meter in diameter. So these very tiny wires act like semiconducting channels that rapidly conduct electrons. Electricity can be more electricity could pass per area through a nanotube than in silicon. And you can also rapidly switch nanotubes between this on conducting state and this off insulating state with less voltage, which means you use less power. These combination of attributes make them ideal for high speed, low energy electronics, which is exactly what we need. So nanotubes, even though we know they're better than silicon, there's been no commercially viable way for using them in an industrial process that's been developed yet. And the reason is that in their raw form, nanotubes look like what's in the upper left here, this tangled, disordered mess that just does not conduct electricity well. To use nanotubes, we need them like what's shown in the lower left. We need a single layer of nanotubes, very tightly spaced, and importantly, all aligned so that they conduct electricity directionally along their long axis. So creating this bottom left cartoon in real life has been the challenge that has really inhibited the adoption of nanotubes by industry. So we've developed a commercially viable process for overcoming these challenges and orienting nanotubes. And we have a three-step process. So first we take commercial powders of nanotubes, which contain impurities. We extract the desirable semiconducting nanotubes from those powders using what's called the polymer wrapper. We then create a concentrated ink of these nanotubes, which is shown here in purple. And then we deposit these inks in the form of aligned arrays on substrates using one of two methods. The first method that we developed is to rapidly flow the ink over the substrate. A second method is to pull a substrate out through a thin layer of this ink that's suspended on another solvent that's immiscible, such as water. This is all done using inexpensive, very simple solvent-based methods. So our process leverages phenomena of chemistry, self-assembly, and fluid flow dynamics for the rapid and low-cost assembly of nanotubes with unparalleled control over their order. We accomplish this using mild process conditions, and we can ultimately create wafers and electronic components that can be directly integrated into chips and devices using equipment already in semiconductor fabs. So our work will impact the semiconductor electronics market in a number of areas. One is in RF electronics. So this is high-speed electronics in your cell phone, for example, that communicates between your phone and the cell tower. The logic chips are the brains of all your devices. And nanotubes even have potential in future emerging applications like semiconductor biosensors or transparent, flexible, or even stretchable devices that just aren't possible with incumbent materials. So we've already used our methods to create aligned nanotubes uniformly on silicon and quartz wafers on a 4-inch, 10-centimeter scale. And we've created field effect transistors, which are the most basic element of a computer chip that have outperformed silicon in terms of electrical current density. Ultimately, devices 10 times faster that use the same power consumption, or devices that have the same speed but that use 1/10 the power will be viable. So this tech has been developed by a world-class team of experts we've registered over 20 patents collectively and over 200 publications. So I'm a professor of materials science and engineering, and I'm an expert in nanotube and electronics device research. My close collaborator, Professor Pat Gopalan, is also in the materials science and engineering department at UW-Madison, and she's a polymer chemist, a nanotube expert as well. We're working closely with an industry advisor, Jeff Moore, who has founded and exited several advanced materials university spinouts. And Sean Foradori, who's here, is a PhD student in my lab who has over 20 years of industrial manufacturing and management experience in the chemical, food, and automotive sectors. So this tech has been developed over 8 years of research supported by the National Science Foundation and WARF. It's protected by 7 patents and is beginning to catch the eyes of major industry players. So this nanotube alignment process that we've invented promises to enable an order of magnitude leap in an industry where progress has stagnated due to the limitations of incumbent materials. We want to take this technology to market, and are looking for an experienced entrepreneur to help start a company. And we are looking for introductions to directors in R&D positions, new product development divisions, in companies in the semiconductor, RF display, and biosensor spaces. Thank you.